It seems that there's a lot of things that are
Hello and welcome to Colloquium.
explored, and yet we're just going through the
Our speaker today is Professor Townsend from the Department of Mathematics. Alex is a student of Nick Griffin. His PhD is from Oxford University. He did his postdoc at MIT, and we were very happy to catch his eye when he was looking for a job. This is his first year at Cornell, and he is already a very popular advisor for camp students and a very popular speaker. I'm not sure how many talks have been given in seminars so far, but suffices to say that he's giving two in the span of the next 3 days. So this one, and Monday he's giving another talk in SCAM seminars, Scientific Computing and Numerics. And the title of his other talk is How to Write the Great...
or lessons from the last 100 years in numerical algebra.
So Alex is currently teaching the course about the 10 greatest algorithms of the 20th century, and the talk is supposed to tell you and all of us how to write a paper which will be in that category for the 21st century. I recommend that other talk as well. Without further ado.
So, why are so many matrices of low rank? Low rank matrices appear in my world everywhere. I see them wherever I look. They're in particle simulations, the fast multipole method. That's working because there are low rank matrices. Whenever you solve an elliptic PDE on a simple geometry, out pops a low rank matrix. The solution usually is low rank if the right hand side is smooth. Smooth functions are low rank. Hierarchical matrices use low rank off diagonal blocks. Multilinear algebra and tensor compression is all about low rank matrices and tensors. Krylov methods, they need low rank matrices to get their convergence from Krylov matrices. Fast transforms, they need, a lot of them use low rank matrices to get their speed. And I wanted to understand why this is. Is there some fundamental underlying phenomenon that's causing low rank matrices to appear in control theory, in statistics, in machine learning? I'm not an expert in all those areas, so I'm going to focus on computational math and try to understand why low rank matrices appear there. But if you're an expert in one of those other fields, I hope you could raise your hand and make comments about why this may or may not translate into your field. So this is joint work with Gil Strang. Gil Strang was basically my mentor at MIT, who asked me continually why. He was the why man, and he really made sure that I answered the why question here. Because before I was good at how to exploit low rank matrices, but not why they existed in the first place. And Bernard Beckerman is an expert in potential theory and rational functions. That's going to come up too. So if you're somebody that likes to look at the slides as we follow, there's a URL down there you can type in your slides. The slides will pop up on your computer. Okay. I should say this is a really personal question because throughout my PhD work, I was exploiting low rank. In that case, in functions, which is very similar to in matrices. And I did loads of things with low rank functions. I did global optimization. Here is a very complicated oscillatory function that has lots of local minima and maxima. And there's the black dots. And the object of the game is to find the red dots. And low rank techniques happen to be key to making that efficient. Or whether you're doing vector calculus, I did a load of work on how low rank can be exploited in vector calculus to speed up computations, or how to visualize complex analysis. So I knew the how, but then I never knew the why. And Nick Griffin joked with me that if I didn't understand the why, I wouldn't be allowed to graduate. So I got very concerned about it, and I never solved the problem. In fact, I went into my D.Phil exam, the PhD B exam, which is the equivalent here, and I didn't know the answer to this fundamental question, which was the basis of my whole thesis. my whole thesis was the assumption that most functions or matrices in practice are low rank, or the ones that I cared about, and I didn't have an answer why that would even be true. So I was dreading the question in my D.Phil exam, which by the way is not like a B exam here, it's a real exam. You can't bring a smile, you can't bring a cake. It's a really formal event, and I was scared of the question, why are so many of your functions low rank? And if so, I was frightened that my graduation would be delayed, as my supervisor predicted if that came up. Thankfully, that question did not come up. But as soon as they signed the papers, my examiners, and handed in the document, I asked them, do they know why so many functions are low rank? And they didn't give me very satisfactory answers. So, I mean, the problem was very, very embarrassing, to the level of the simple stuff I just didn't understand why. So, for example, if I take this function, you can think of this as a matrix 1 over I plus j. So the ij entry is 1 over I plus j. It's a very simple matrix, it's a very simple function. If I tried this in this piece of software that I wrote and calculate, tell me what the rank of that function is. Mathematically, that rank is infinity. If I make this matrix, infinity by infinity, large, the rank of that matrix will be infinity. However, when I compute this on a computer to 16 digits of accuracy, that's what a computer is working with, I get 8. And I didn't understand how you could go from, or the mechanism that led you from infinity to 8. And it wasn't until May last year that I actually understood why there should be an 8 there. I actually understood why it needs to be less than or equal to 11. So that's the theory I'm going to introduce today. Why this is less than 11, not infinity. Thankfully, I did graduate before May 2016, otherwise I'd only just got out of Oxford. Okay. So let's go back a step and just remind ourselves what the mathematical rank of a matrix is. So I would like you to think of X as your favorite low rank matrix, if you have one. And for example, that matrix is in general rectangular. And you'll remember that we say the rank of a matrix is K if we can write it down as a sum of rank 1 matrices. And a rank 1 matrix is just a matrix formed by the outer product of two vectors. So you can see here I'm summing up K rank 1 matrices. Assigned to every matrix X is a sequence of numbers, the singular values of X. These tell you how many terms you need to write down X exactly as a low rank expression like here. So an equivalent characterization of the rank of X is K is that K is the smallest integer so that the K plus 1 singular value is 0. If you don't know singular values, you take X transpose X of your favorite matrix and ask about the eigenvalues of that. The eigenvalues of X transpose X are square root. Are the same as singular values. Okay, and I like plotting singular values to have a look at them. So here is a random normal distributed 10 by 10 matrix. Here's the 10 singular values. They drop down a little bit. Hopefully you can see the axis. They drop down by orders of about 10 to the 3. So it's like 3 levels of drop there. And if I take a matrix of all ones, of course that can be written as a single, that's of rank 1. So there's one singular value which is above 0, and I've plotted the ones down here at machine precision so that we can still see them, but they're really zeros. So we can use these graphs to tell us what the rank of a matrix X actually is. So I like trying to understand what they are visually. So what do low rank matrices actually look like? And I like introducing them by just looking at flags. Surprisingly, a lot of flags are low rank. I don't know why, maybe because they're simple. So I've taken here flags that are only of 2 colors, so it's easier to interpret what I mean by rank in this sense. So any entry which is white here, you can think of as a 0, and any entry which is colored, you can think of as a 1. And so you could write down, let's say, a 6 by 10 matrix for each of these flags. So which ones are low rank and which ones aren't, and what is the rank of these 3 flags? Well, the Austrian flag is really easy, because that's definitely rank 1, and we know that because all the columns are the same. Right? So that's definitely got rank 1, and that means we could write it like this. If I was sending the Australian flag to my friend, I could instead of sending them the whole flag, I can send them the 2 vectors. And that would be the same. Right? They can reconstruct the flag from that. And so there we've just seen how low rank can compress a matrix down. Right? Or the Greek flag, which is more interesting. Actually, can anyone see what the rank is? 3. I send it as a stripy matrix, and then another one with a little block at the top here, and then a 3 dots left. So that you can see I take the stripes out, the fully striped flag, that's this guy, and then I try to patch up what's left, which is just in the top block here. That's where I made the error, right, when I sent the stripy flag. And so I just color-coded the 3 numbers that you need to send. So you could send the Greek flag as these 6 vectors instead of the whole flag, and you'll get yourself some compression. So many extremely low rank matrices are aligned to the grid, just as the Austria and Greek flags are. The Scottish flag is almost a full rank, but not quite, because there's symmetry. For instance, the top half of this matrix, all those rows, are the same as the bottom half. And it's the same with the columns. Half the columns are repeated because of the symmetry. So the rank of that is half of the size of the number of rows. Now, I'm not interested in low rank matrices like this, obviously. Most matrices that I deal with are not mathematically of low rank in this sense. They're in the example that I had with the function 1 over x plus y, where mathematically they're of full rank, or infinite rank. But when I put them on a computer numerically, they happen to be of low rank. So I'm interested more in numerical rank, not mathematical rank. And numerical rank's very similar. Here's touchdown the bear, the Cornell bear. Here's the image. This is the full image, pixelated. And here's the rank 1 approximation to touchdown the bear. And you can see it's rank 1 because it's aligning with the grid, with the columns and rows. And here's rank 35 touchdown. And you can see they're about the same. How did I know how to make them the same? How did I know how to choose 35? I can look at the singular value plot again and decide what number I need. For example, here's the singular values of touchdown the bear. And I reckoned that on a slide you could only see about a 1% error. So I drew a line across here and pushed it down and made sure that I only kept the 35 singular values that live above that line. That's how I got 35. In fact, if you could see this up close, maybe you can see that the eye is all smudged and out of focus. If I actually gave you a printout, you'd be able to see the difference between these two. And I would drop my epsilon down to 10 to the minus 3. Okay. The actual definition of numerical rank is I give you an epsilon. For me, I'm thinking epsilon is 15 digits or 16 digits. So 10 to the minus 15. In an image case, I chose 10 to the minus 2 here. And the epsilon rank of a matrix is just the smallest number that I can get away with, which means that I can approximate x by a rank k matrix and only give up an error of epsilon. So if I'm on a computer, I choose 10 to the minus 15. Because of rounding errors on a computer and floating point arithmetic, our computer's not going to know the difference, if epsilon is 10 to the minus 15, between x and xk. And instead of working with x, I can work with xk, and nothing will change. The number that I get out at the bottom will only change by round-off errors. Right? And I may have saved myself a huge amount of computation. One, because I've compressed it, and another reason is because when I do operations on x, I will do them on xk instead, and it will be much faster to do that, because xk is of rank k. Okay? So these plots are a visual aspect. I'm just going to keep these guys up here for whatever epsilon I choose. For the rest of my talk, you should think of epsilon as 10 to the minus 15. Just to make sure that I'm answering a question that's meaningful here, you might say that, well, maybe the reason that all the matrices you have are low rank is because just the average matrix might be of low rank. So I'm just making sure that that's not the case here. So back in 1988, Alan Adelman wrote down a theorem, which I just reused, packaged his result to work with numerical rank. He wrote it down with condition numbers. And it says the following, which I'll just put in layman terms. If I generate 1,000 by 1,000 matrices from the beginning of time, every nanosecond, all the way up to the present day, I still wouldn't have expected to see a single matrix that was rank deficient, which means the last singular value on that plot was below epsilon, where epsilon is 10 to the minus 15. Not a single one in expectation. That's how extraordinarily rare a low rank matrix should be. And I don't want just one singular value to drop below epsilon. That's not going to save me much if I cut that off. I want almost all of them. I only want a small number above epsilon. So you can just imagine how extraordinarily rare such matrices are if I'm thinking of them as generated by a random number. Low rank matrices are definitely not average in the sense of random number generation. So this is the exact result here. This is what I'm referring to here. The probability of getting a matrix which is rank deficient when epsilon is 10 to the minus 15 and n is 1,000 is 10 to the minus 26. It's a tiny number. So random matrices are almost surely of full rank. So that cannot be the reason. So I started, after my D.Phil defense, I started asking people why they think matrices are low rank. And I got a whole spray of answers. So I thought I would summarize them, which I was going to do here. I got answers like the world is smooth, which means that if I sample a smooth function and make it a matrix, so your function is like a polynomial or analytic function, then John Reed in 1983 proved that this x has low rank in the sense that its singular values decay rapidly. The smoother f, the faster the singular values decay. The people in the fast multipole method community told me that the world is well separated, which what they meant by that is if two galaxies are separated apart and I'm looking at the gravitational force between them, I can replace one galaxy essentially by a superparticle and calculate the gravitational forces between that superparticle and the galaxy of interest, rather than every single pairwise interaction. And that is a case of low rank approximation. Statistics people were telling me that the columns and rows are correlated, which is just the same definition of low rank, essentially. Sloppy model people, there's a great quote where they actually say essentially that the world is VANDERMONDE. They think that the reason that every matrix is low rank is because they're all associated to VANDERMONDE matrices. And there's one example that I've been using to tell them that we need a new reason here. And the canonical reason that breaks a lot of these reasons is the Hilbert matrix, which has been studied since 1970 as interest of why this matrix is so badly ill-conditioned, or equivalently, why the singular values decay so fast. The mathematical rank is full. The numerical rank, if I calculate with the plot and chop, when epsilon is 10 to the minus 15, is 28. If I do the smoothness argument on this, so that's John Reed's theorem, I apply it. So f, this is a function, right? 1 over x plus y minus 1. I sample it. I know that f has some smoothness. It's an analytical function. I can go through his bounds, and I get 790, which doesn't explain the 28. That's my point. And you can do a little better here if you refine what John Reed did and get 86. Still, you have to work very hard for that. The reason that I'm going to suggest today gets you 34, which is a lot more reasonable as a bound on 28. So let me go back to the what kind of matrices are low rank. Vandermonde matrices are low rank. Cauchy matrices are low rank, and we're going to be able to explain all these, assuming that the xj's and the yj's are separated. Positive definite Hankel matrices are low rank. These are matrices that are constant along anti-diagonals and have positive eigenvalues. Solutions to Poisson's equation, so elliptic PDEs with square domains, are low rank in the sense that if I sample the solution, I get a low rank matrix. I had a summer student intern working here that figured out that many non-uniform transforms have low rank. And the state of the art for showing something is low rank is literally look at the plot and watch them decay. It's like not insightful, because I go to my next application, I see the plot decay again, I decide I have a low rank matrix, I apply the techniques, and then I move on. There's no connection between different applications. Okay, so let's get into it. So if these are all the reasons, the world is smooth, the world is well separated, my reason is the world is Sylvester. Okay? So what do I mean by that? I mean that all these matrices, all the ones I showed, Vandermonde, Hankel, Krylov, in fact, I think every single low-rank matrix, in some sense, fits into this framework, satisfies a Sylvester matrix equation. So here's your X, here's your matrix you're thinking about. Maybe you can think online now what your A and B are, so that AX minus XB equals some F, where F is low rank, which I'll get to. So for example, for the Hilbert case, right, this is the matrix, the entries of that matrix. If I multiply on the left by this diagonal matrix, and I multiply on the right by this diagonal matrix, so A is this guy and B is this guy, diagonal matrices, I get the matrix of all ones. Why is that? Because I multiplied the ij entry by I plus j minus 1. That's what that's doing. So this is A, this is B, and this is of low rank, because it's the matrix of all ones, which is rank 1. For the Vandermonde case, that also satisfies the Sylvester matrix equation, as now I know it must do. For example, if I multiply on the left by this matrix, this diagonal matrix, that multiplies each column up by 1, by x. And if I do a circumshift of the columns, so the first column goes to the second, second to third, and the last one that drops off, the end, comes back to the first, then what I see is that zeroes out everything. This combination zeroes out, apart from the first column where I did that thing that dropped off the end came back to the front. Everything else was a multiple by x, because if I shift this up by 1, I was basically multiplied by x. So I think the reason that low rank matrices exist, and there's so many of them, is because so many satisfy this Sylvester matrix equation. So why is that? Why would satisfying this equation be meaningful or allow you to do anything about low rank? And here's the reason, which I'm just going to state for now. Provided the X matrix of interest satisfies this equation, and your matrix A and B are normal, so let's just think of them as symmetric, perhaps. It's a little more general than that. And the right-hand side is of low rank, let's say R. What it allows me to do is to bound the singular values of X by this crazy number called a ZOLOTAREV number with this norm of X at the right-hand side here. Now, it looks like this theorem does absolutely nothing for you. You've taken something which is pretty constructive, which is like calculate the singular values of a matrix, we can do that, to understanding this more abstract number called a ZOLOTAREV number. So for example, for the Hilbert matrix again, the D over here is my A. This ZOLOTAREV number is based on the eigenvalues of A, so the spectrum of A, and the spectrum of B. So we know what D lives in, and we know what this other D, minus D, lives in. So what this tells us, here's the bound that you get from this theorem, and here's the plots of the singular values. So from this, I can see what I wrote down, which is the 34 number. You can see why it's 28, the numerical rank of the Hilbert, because the first one that drops off the end is around 28 in the singular values. And you can also see from this bound that we know this, the dots must blow below that bound. So here's 34 when it crosses 10 to the minus 15. That's how we got 34. Okay, I'm going to get into this now. So what is a ZOLOTAREV number? And then I'll explain why they come up. What is a ZOLOTAREV number? It's a really relatively it's more abstract than the singular value, that's for sure. It was invented, let's say, by ZOLOTAREV, who was a student of Chebyshev. They were both interested in extremal problems, like best fit. So they were interested in best fit rationals, best fit polynomial fits, and best fit rationals is what comes up here to bound singular values. So the ZOLOTAREV number here, this number here, is actually a rational approximation problem. Okay, so here is a rational approximation problem on the discrete sets sigma A and sigma B. And the problem is the following. Design a rational function, which is a polynomial of degree k over a polynomial of degree k, that fits, that does the following, is as large as possible on the red dots, and is as small at the same time on the blue dots here, and it's the ratio that matters. That's an extremal problem, so you can come up with lots of candidates, right? But you've got to find the best fit, the one that does that ratio the best. And that's going to be written down in this way. This problem of just like having the discrete numbers is really difficult. So often I just draw a circle around the spectrum of A and the spectrum of B and make them continuous plates. And that simplifies a lot of things. For example, if I've made them into these closed sets, then provided I've designed a rational function which is large on this circle and small on this circle, it's going to be small on the dots and large on the other dots too. Right? So often I'm trying to make a rational function as large as possible on a circle or an integral or some continuous region and as small as possible on another region. And that will give us, if we understand that rational approximation problem, that will give us a bound on some singular values, provided x satisfies that's the best one. Does that make sense, what we're trying to do here? Okay, maybe we can do some examples in a sec.
Can a rational function be small on a circle and large inside the circle if it has a hole on the inside of that circle?
Yeah, so I meant this is a closed region. So maybe I should have said disk. Yeah, so
got it.
I'm trying to make a rational function as small as possible on this disk and as large as possible on this other disk. Exactly. Yeah.
Can I ask something?
Yeah.
So when you wrote down that, I guess you're going to talk a lot more about the Sylvester equation and how we should think about it?
Yeah.
All right, maybe I won't ask anything.
What was your question?
Well, I just want to know how I should think about it. Like, is it a generalization of saying that, so if I even understand the statement, it's that given a matrix X, I can find an A and a B such that I can then write AX minus XB is low rank.
Yes.
That's what it means. It's a property of X that there exists an A and a B.
Yes.
Okay. So does it mean, but then sometimes you've shown the A and the B to be the same matrix, like it was D in some case.
Yeah.
So then it looks kind of like X kind of commutes with some matrix D.
Yes.
Sort of, really, if you think of F as being 0.
So I think if A and B,
I don't know how to think about it.
I think if A and B is connecting the row information with the column information. You see, AX can only modify rows of X,
Okay.
and B can only modify columns. And if I'm allowed to do this small modification of the rows and the columns and get something which is low rank, then I can show that X is itself low rank. In the simple case where, let's say, A is the identity and B is 0, right? Then I just have X equals F. Then I know, that's giving me already that the columns and the rows are somehow correlated, or the columns are all correlated, the rows are all correlated. Whereas if this is a slightly more general statement than that, allowing me to slightly modify the rows, slightly modify the columns.
Okay, good, thank you.
So when A and B have to have full rank, you can't take A and B equals 0.
You can take A and B to be 0. Or if you take A to B, you've got to have this. So this
Oh, the numbers
ZOLOTAREV
won't tell me anything. This won't tell me.
it won't tell you anything.
Gotcha.
You can pick whatever you like for A
Right,
and B.
right.
The problem is to pick the right A and B that makes sure that F is simple enough to understand, in particular, simpler than X to understand. Right? So, for instance, in that Hilbert case, we didn't understand Hilbert, but we understand in the matrix of all ones. Right? So that was a good move. I could choose a random A and a random B, and it wouldn't tell me anything. And the F wouldn't be low rank in that case either. Okay. I can come back to this if there's questions. This is just telling me that, or maybe I'll say the right word. How to think of this ZOLOTAREV number was what I was trying to get at here. So the ZOLOTAREV number is, so the beauty of looking at this ZOLOTAREV number over singular values is the ZOLOTAREV number is all about potential theory. It's all about rational approximation. So there's been lots of work that's been done on the ZOLOTAREV number because people cared about it from 1877 onwards, so they worked at it. So how you should think about it is the following. I have a pocket full of electrons, negatively charged, and I have a pocket full of positively charged. So I have a pocket full of negative, a pocket full of positive, and I throw them on these two plates, circular plates. So let's say the negative charges go here, the positive charges go here. If those two plates are far away from each other, you should now think about these charges moving to equilibrium. Okay? Just watching them move to equilibrium. If the two plates are far away, the energy that they have is large because the positive electrons over in this plate and the negative electrons over in this plate can't use each other because they're not close enough to lower their energy. And that turns out to be a good case for ZOLOTAREV. So large energy means rational approximation. There's a good rational approximation that's small on this region and large on this. If those plates are really close together, now the positive and negative charges can start using each other to minimize what's called their condenser energy. And if that minimum condenser energy is small, that's bad news for rational approximation. Because it's harder to come up with a function, a rational function, that's small on this region and large on this region if they're close. And that electron interpretation is precise. Is that the minimum condenser energy from those two plates tells me exactly how the rational function converges. Right? So if I have, in this case, if I have k electrons and k positively charged particles and I put them on each plate, that will actually tell me what zk is if I just let them settle down to equilibrium. So that gives us like a physical meaning to what this ZOLOTAREV number is, which means we can actually calculate it. Sometimes we can get bounds for it, they're analytical, because of this connection. And loads of people worked on this. So it's better to work with examples. So let's go back and think about examples. So the Hilbert matrix, the classic one that we've got to understand because everyone brings this one up. So you remember it satisfies this Sylvester equation. What are the eigenvalues of A? They're equally spaced numbers between a half and n minus 2. So they're in this interval here. They lie on this line between a half and n minus 2. And remember, I'm going to do the simplification, which makes it a closed interval. So I'm going to just draw a closed interval here. And remember the B's, that has equally spaced eigenvalues on minus a half to minus n plus a half. So the eigenvalues of B lie somewhere in here. So I'll just make it an interval. And the question, remember, for ZOLOTAREV is, can I make a rational function as large as possible in this region and as small as possible in this region? ZOLOTAREV in 1877 gave the answer, analytically, in terms of elliptic functions. And here is that answer. Okay, so I've drawn this so they're not too large, but it's tiny over here. Right? Because it's the ratio that matters, remember, between these two regions. So this is the best fit line with a certain k. I forget what it is, but for 1k, we can work it out from the number of poles. And this allows us to get a bound, if we go through this emotions of throwing electrons on each interval, to get a bound on this ZOLOTAREV number, which is explicit, very simple in terms of logs. So we can just rearrange things. This is telling us how fast the singular values decay. We're just plotting that line going down. And this allows us to get a bound on the numerical rank of the Hilbert matrix. So what is this line here? This line is this function right here. And I got that from actually potential theory. That's where that comes from, right here. So this is how well you can fit a rational function to these two intervals as k increases, right? And k equals 1 to 35. Once you give me k equals 34 in this case, I can get a rational function which is bigger than 1 on the size of b and below machine precision on the size of a. And that allows us to get this very explicit bound on the numerical rank, which gives us 34. When I type in epsilon equals 10 to the minus 15 and n equals 1,000. Sorry. What about other things like the Cauchy matrix? The Cauchy matrix is made up of a very simple, it's very close to the function that I wanted to understand, which was 8, and I got 11. It looks like this, xi minus yj. It's the difference of two things. It's like 1 over r kernel. Of course, it satisfies a very similar Sylvester equation to Hilbert. If I throw down a diagonal matrix here and a diagonal matrix here like this, then I'm timesing the numerator here by xi minus yj, and I get the ones. So here's the eigenvalues of in this case, which way around is it? A. Here's the eigenvalues of b, and I'm going to map them so I can look at potential theory. I get a number out, and I get bounds from that. Now, the nice thing here is that I got excited when I saw this, because fast multipole method is related to the kernel, and they use the separation of two intervals based on the minimum separation distance. And here I didn't get the minimum separation distance. I got this thing called a cross ratio, which is a very different quantity. And I thought, okay, I can actually improve the fast multipole method a little bit by using this. Turns out the fast multipole method was actually already using this. So I don't know how they knew about that. But you can see how tight the bounds are for different intervals. What about the Vandermonde case? In this case, we have diagonal and this circumshift. If n is even, then here is so these xi's, I'm just assuming to be real numbers, they can be anywhere. They lie on this blue line. And this circumshift matrix, that if n is even, has roots of unity shifted away from the origin, so that they live on these two arcs that are separated from the real line. That's key, right? Because now my task is to find a rational function which is as small as possible on this blue line and as large as possible on these two arcs. So what do? I throw down electrons and positively charged particles, and I let them settle, and from that I can get bounds. Here you get the bound on this guy, like this. And you can notice that now this bound depends on actually n, because as n increases here, this arc approaches the real line very slowly, like 1 over n. And so you can go through and get them. And because of this encroachment of the arc to the real line, the bounds aren't as good. And I don't know how to get any better. So this is the best I can do right now. But these are the singular values decay. I've got some geometric bound, but they're faster than that. I don't know how to do that. Are there any questions about the 3 examples? Does it make sense? Yeah.
Okay, I have a question. In the example of the Cauchy matrix,
Yeah.
if you had chosen your x and y values to be highly interlaced, it
Yeah.
seems like this would give a very weak bound on the numerical rank.
Yes.
Is the numerical rank of that matrix actually high when you
Yes.
look it up?
If I interlace them like this, the Cauchy matrix is a full rank if they're completely interlaced. Because essentially, potential theory, I've got to fit a rational function which is large, small, large, small, large, small. It has to be extremely symmetry to capture that. And therefore, I need basically the number of degrees that I need in the rational function is n. It's a full degree. If they're only as slightly, as these two eigenvalues start interlacing and crossing, the rank slowly, steadily grows. until they've crossed completely. Yeah, thanks. Yeah, so there is this separation condition here on this guy, which you can see from.
So, excuse me.
Yeah.
So actually, the case when B is equal to A is the bad case, which is the case of commuting, right?
B equals to A.
And in the matrix, in the definition, big B equal.
Yeah, in this case, if these numbers are equal to these numbers, then this matrix doesn't make sense.
I mean, in general, in the definition of this number was the Z.
Yeah, if A equals B,
Nothing
can be said.
Which is exactly the case of commutation. I mean,
exactly in the case of commutation, I agree.
right.
Yeah,
Because the spectrum overlaps. I mean,
because the spectrum is the same. And in fact, then the Sylvester equation doesn't have a unique solution. So
okay.
we get into more trickiness than even what I'm saying here. Are there any more questions? Yeah.
Should I think for a fixed x and a fixed rank target, are there a canonical family of A and B that will provide kind of a minimum or like an optimizing this bound you get from the ZOLOTAREV?
I should say, so the art in the science here is you've got to come as a human being with clever A, B, and F.
Okay.
I don't know a generic way to get yourselves useful A, B, and F. I can generate them, but they're not useful.
Okay.
So the ingenuity here has to be with coming up with triple A, B, and F. Once you've done that, it's a mechanical problem to get out the bounds, because it's all about potential theory and rational approximation. It's just turning handles. But you've got to come up with clever A, B first.
Okay.
So that's the task really now.
And that's the one you feel maybe you haven't totally succeeded on in this case?
So, yeah, in this case, maybe I could choose a better A and B so that I don't get this encroachment. But our theory here only ever gives us geometric decay, gives us lines on the band. And you can see here, the Vandermonde case is faster than a straight line. So that's telling me that it's the discrete part of the spectrum. The fact that these are dots, not lines, because remember my first assumption was to make I make dot lines and regions. This is telling me that if I want to get a better bound on this, I've got to start thinking discretely. I've got to do ZOLOTAREV, which is called discrete ZOLOTAREV numbers. And at that point, I'm very scared because it's very hard. And not much work has been done on discrete ZOLOTAREV numbers.
Could you also take a function of the matrix if it's positive definite? You could try taking a logarithm and doing the same thing for the logarithm of the matrix, but again with a smeared out thing.
Yeah, you can do that. Well, in fact, for the positive definite Hankel matrices, that's pretty close to how we get the bound, which I haven't put on these slides. Yeah. I wanted to say at this point that low rank matrices are not always good for you. Right? You don't think that they're always good. They're not always. It depends what you want to do. For instance, Vandermonde matrices, they always come up in polynomial interpolation. If you want to interpolate a polynomial, you usually write down at the points x, I, you usually write down a Vandermonde system to solve as a linear system. This is telling us here that if you've chosen those nodes, those interpolation points to be real, and you're in the monomial basis, you're guaranteed to have exponential ill conditioning, which people in my field already knew. I'm just making the point that low-rank matrices are not always good for you. If you want to solve a linear system, you don't want a low-rank matrix, because that's ill-conditioned. So this is also telling me that the condition number of the Vandermonde matrix for any real nodes is exponentially ill-conditioned. Bad news. It means polynomial interpolation with monomials and real interpolation nodes is never going to work numerically, because it's very sensitive. I wanted to give just a hint at how you get from the Sylvester matrix equation to ZOLOTAREV. Because many of you might know the way we do it. If David Binder was in the room, I'm sure he would. He knows this because I spoke. So how does it work? So the Sylvester matrix equation looks like this. And you'll notice that if you choose any pj or any qj, any numbers, and you can shift these matrices around, x will still satisfy, it will end up satisfying this equation right here. Okay? for any P in Q. Right, they're just the same. They're almost the same statement, really written. And if you know alternating direction implicit method, a really classic algorithm from 1955, they had a really great way of solving such equations, such Sylvester equations. And that's the one we're using to generate these bounds, to generate the ZOLOTAREV function. So what did they do? They basically fixed the columns of x and sweeped information across the rows, and then they fixed the rows of x and sweeped information across the columns, and then they iterate between those two. They alternate the directions of sweeping information in x, and that's being used when you like fix this term, use this term, that updates the rows, do this term, fix this term, update this term, that updates the columns. And they did this in an iterative fashion to get the solution of the Sylvester matrix equation. And the actual algorithm they wrote down is this. You can see that the first step is updating the rows, and the second step is updating the columns. Our spot, this is our only spot at getting ZOLOTAREV out, was that if I go through this algorithm and look at the rank of the iterates that ADI, alternating direction implicit method, generates, it generates low rank matrices that are really good at approximating x, because that's its task. Its task is to not use too many iterations and solve the Sylvester matrix equation. And so that's what we use. If you choose these shifts here, these Qs, to be perfect, the optimal shifts, you get ZOLOTAREV out. That's our only spot here. So what my point is here is, not only do we have a bound on the singular values, if you want a low rank matrix which delivers you that bound, I can compute it. It's just ADI. It's just a numerical scheme that's been known since 1955. I can give it to you. I can give you the matrix which delivers the bound. So that was my, and it's a very simple numerical algorithm. Okay. So up to now, we have a reason why matrices are low rank, but maybe it's not the reason. Maybe it's just another reason in the bag. Right? I don't want, yeah.
So something about the last slide I didn't quite understand. The way the ZOLOTAREV numbers came in was not very apparent. Does it have to do with the choice of the optimal shifts P and Q?
Yes. So how it works is, if you know the ZOLOTAREV, the rational function which delivers you the ZOLOTAREV number, I forget which way around. The P's should probably be the poles of that function, and the Q's are zeros. It's not immediate. You have to go through an error to get that. But if you choose those, once you give me the rational, I got the shifts. I use the shifts, I get out ZOLOTAREV. That's the way to create matrices which deliver that back. So right now we have this reason. It may not be the master reason. It might be just another reason. There may be low-rank matrices out there that don't fit into this framework. So I want to try to convince you that that's not the case. In fact, every low-rank matrix in my world fits into a Sylvester matrix equation, and the task for me is just to figure out the A, B, and F that does that. So this is what's called log-rank matrices. All log-rank matrices fit into a Sylvester equation. So let me tell you what a log-rank matrix is. So right now we have this, the world is Sylvester. We have, if it satisfies this, where this right-hand side is very small, then X should be low rank if these eigenvalues of A and B are well separated. There's loads of examples that don't fit. For example, which is very disappointing for me, the 1 over R squared kernel, like differences, that comes up in gravity simulations. I really want to get that one. Also the Hilbert, if I just square that number, it doesn't fit in my frame. So I feel like I'm just like all the other people. I'm just like John Reed. I just have a smoothness of number. I don't have the master reason, which is disappointing. I want the reason. So let me tell you what a log rank matrix is, because I've got to define that now. A log rank, so of course, if I take a full rank matrix and I want to store it, I've got to store every entry. If I want to do a map vec, I've got to do something on every entry. If it's in low rank form, I can speed that up. That's why I care about low rank. For instance, I only have to store the k columns, which are of length m, and the k rows, which are of length n. So that's k n plus n. And if I want to do a map vec, I only have to deal with those entries. So I'm going to define these matrices, and these are the matrices that I always work with. I've never done low rank techniques on a matrix which doesn't fit in this framework. The reason is that there may be other, if it's not log rank in this sense, there may be other ways, other techniques that are better for you. than low rank. So what it means is that the rank grows slowly. So the epsilon rank grows slowly. So it grows very slowly with n, like log n. And so you can't have square root n here, because that's going to go up here and give you n to the 3 over 2. And it's going to grow slowly as epsilon goes down too. These singular values have to decay fast. That's a equivalent way of saying it. Not quite geometrically. It can just go a little slower than that, but not much. That's what this is saying. So for instance, this includes the Hilbert matrix. That's when P equals 1 and Q equals 1. And it also includes all these other ones that I want to include, like the fast multipole gravitational kernel. Right? Like this. So that's where P is, I think, 2 and Q is. So what's the problem with what we have right now is the following. If the rank of this right-hand side was, let's say, n, I would come to this step here and use my ZOLOTAREV bounds, but it wouldn't tell me anything, because I'm using the mathematical rank of the right-hand side, f. Right? So I'd stick an n here, and that wouldn't tell me anything, because x is only of size m by n. That's all it is. So that would tell me nothing of the singular values that I care about. So what Heather did is notice or spot that the matrix here, in all these other cases, this matrix, is of mathematical rank n, maybe full rank, but numerical rank small. Can we use the fact that the singular values of f itself also decay to improve the bound? And if you do that, you start incorporating every single log rank matrix. So for example, this one I care about, which is 1 over r squared, looks like this if I do the complex analysis. I can use this diagonal matrix and this diagonal matrix to get it to Cauchy, which is just 1 over omega I minus z on j. That's what this guy is, right? Because I'm going to times the top by omega conjugate minus z conjugate. And the fact that this, we already know that the singular values of Cn decay. Heather can use that to get to better singular value decay for the 1 over r squared kernel, which I really care about. So, provided all these things are separated. So this is explaining fast multipole, if we're going to go into that. But I'm going to give a lecture on that very soon in Math 6140, about how this gets you to fast multipole. So what's next? I thought I should tell you. In fact, for me, this has kind of opened up a door, and like the world starts making sense if I start thinking about Sylvester. It's leading to loads of new places where I'm finding low rank structure, and now we can actually exploit it, and we can do it. So Dan Fortunato, who's a grad student of mine I co-supervise in Harvard, is using this to generate really fast numerical simulations of PDEs. And low rank is the key, because Poisson's equation, if I go through this, gives me log rank matrices. He's using that fact. Heather's been using her stuff to get sloppy models, to explain the abundance of sloppy models with Jim Slefner. And we just started thinking about why low-rank matrices are found in big data. Madeline has some really good ideas there. And I think Sylvester is the key, perhaps, or maybe something else. So why are so many matrices of low rank? My answer is the world is Sylvester. Don't ask me why Sylvester. I don't know why Sylvester. But if you have a low rank matrix and you have the A, B, and F, I can generate the singular values bounds for you. If you don't know the A, B, and F, we've got to brainstorm. Here's a selection of the bounds that we got so far, but there's many more. If you ever have one of these matrices, you can plug in your numbers and get a really tight or relatively tight bound on numerical rank. Okay. Call me if you have a low rank matrix and maybe an F. Thank you.
So I'm going to ask you a question that might be circumventing 90% of your talk, and I feel that I'm asking just to ask a question. But ironically, I'm teaching the engineering computation class to undergrad engineers, and I have to teach them to love this stuff. And it's not an easy task. And we just talked about condition numbers, and I had the student ask me, why should I care about conditioning? How this going to impact my life? And we're doing least squares, and I said, okay, here's a periodic a signal that's oscillatory but non-periodic. I want to fit it. I start fitting it with polynomials, and you want to add higher order polynomial, like modern polynomial basis functions. And look, boom. And I showed them the VANDERMONDE matrix. Yeah. And most engineering students, I don't know how this room's going to feel about this comment, do not like the concept of eigenvalues and eigenvectors, right? That seems very foreign to them. So just on a pedagogical level, how could you explain just a general idea of low-rank matrices and their numerical challenges to an engineer without really appealing to eigenvalues but still using your ZOLOTAREV framework, right? Because I just said, let's sweep the matrix, let's watch it in MATLAB as we're going higher, like we're watching the angle between two successive column vectors just decaying, getting awful, getting close to your machine epsilon. But you have this cool way of looking at things. Could we minimize reference to eigenvalues, use some of these concepts instructionally for an undergrad?
That's a big question. I'm going to have to. Can I
So maybe we can talk
think about that offline?
Yeah, let's talk about it like
That's a really
one-on-one.
hard question, perhaps, to how to communicate research level math to
Yeah, this is a bigger picture.
undergrad engineers.
So I'll back off and we'll talk about
Let's think about that later.
Yeah, yeah.
No, it's a good suggestion.
Yeah, I have one remark and one question. So this ZOLOTAREV minimization problem only involves the spectrum of A and B.
Yes.
So you have complete freedom over the eigenvectors.
Yes.
And I wonder if you want to somehow right, think of the infimum as like two infimums. One over the spectrum and or supremum, whichever way, and one over the eigenvectors. If one can somehow solve, given the spectrum, one of them explicitly. I mean, or is that right? I was wondering that. And the other question is, maybe I'll let you answer that. I mean, it seemed like
I mean, you can fix the eigenvalues and then try to search for the eigenvectors
given those eigenvalues.
given those eigenvalues, but you've got to make sure the right-hand side is low rank.
Right.
And so far, the easiest way to do this is to remember the A and the B have to be normal in this setting. We can generalize that a little bit, which means they're symmetric. Let's think of them as symmetric. Or more generally.
Yeah.
But
Which is, I mean, I can implement to the eigenvectors, so I just only use orthonormal.
yeah.
Yeah.
Yeah, you can just use orthonormal. I don't know how to do, if that's going to come out with something useful or not.
Because you have one of this classical potential theory problem, but that's just about points and spectrum, and there's nothing of this linear algebra.
Yeah, there's nothing, that's why we got success here. Because we went back to 1877 and all the work that they did, and they were actually bounding singular values for us in special cases. And we could like reuse that machinery in the linear algebra setting. Yeah.
I also had a question, which is probably just a point of clarification. When you say potential theory in 2 dimensions, do you mean you have a logarithmic?
Yeah.
Okay.
So I'm thinking about logarithmic capacity
Right. Okay.
of plates out of a minimum condenser energy, logarithmic condenser energy.
And you say some of this ratio of rational functions that's just the same as minimizing.
It is the same.
Okay. Okay.
Yeah.
Okay.
The potential theory and rational or polynomial approximation has very close connections. So we're really good using that. Yeah.
On the slide where you presented other people's answers,
Yeah.
like the world is Vandermonde or the world is sloppy, it seems like many of those got folded in as special cases of your Sylvester explanation.
Yeah.
But the smoothness one, does that arise as a special case of your Sylvester equation explanation?
No, that's much harder to characterize in terms of Sylvester equations. So I guess that there's still all these definitely translate into Sylvester. This one is a little tricky. In fact, I've been thinking about this in other contexts, and I haven't really got a good answer of how smoothness translates into Sylvester, but it must do, but I don't know. Actually, Madeline has some good answers on that potentially. So maybe wait a couple of weeks and I can answer that one.
But didn't you say something about solutions of Poisson's equation?
Yes.
Did I hear you mention that at some point?
Yeah.
So how much would this generalize to other classical PDEs, like solutions of, I don't know, wave equation, heat equation?
Any uniformly elliptic PDE with a Helmholtz frequency complex will fit into this framework. It's about the spectra of those two. So we have the spectra of the two differential equations called separated spectra. Mm-hmm. That doesn't happen for Helmholtz, where you have high resonance of acoustic scattering. Mm-hmm. It doesn't happen. There's a full rank guy. But in the case of Poisson or stream Poisson, so moving the other direction, that is a case where ADI, alternating direction implicit method, is a good solution technique. It's been applied to the heat equation, but it wouldn't work for the wave function. So we know what classes they apply to.
So, but the heat equation is parabolic.
Yeah.
I think this is why I'm confused. Elliptic, I think of as having no time.
Yeah, there is no time.
So what about all the dynamics in the world? Well, I don't know. I'm just confused. And, I mean, you're making a statement about things that aren't moving, okay.
Yeah.
But lots of things move.
So the original ADI method was proposed for the heat equation as a solution technique for Crank-Nicholson discretizations of the heat equation. So in my sense, if I go through that algorithm, it's going to be generating low rank matrices, assuming the solution on the right hand side is smooth. So therefore, something's going to be low rank in the heat equation. Every time step, it must be low rank. I know it's smooth. I know it's a smooth function in the T profile. So I already know from John Reed that there's something low rank there.
I mean, it has an elliptic generator.
Right, yes.
So that might be.
Yeah. And if I solve it with a time-stepping scheme, I'm solving screen class, not how class. Tells me that there's got to be low rank there, but I haven't worked through it.
Can you tell us the history? Oh, sorry. Go ahead.
Go ahead with one
Well,
more
just you
question.
mentioned Sylvester, but you never told us why Sylvester was thinking about it.
I don't know why Sylvester was thinking about it.
Oh, okay.
I've been trying to find out the answer. If anyone knows, I would love to know why Sylvester wrote down the Sylvester matrix equation. Or did he write down the Sylvester matrix equation, or did someone else? Because I can't even show that Sylvester came up with the Sylvester matrix equation. I don't know what paper he did that. I don't know why it's called the Sylvester matrix equation. If someone knows, I would love to know.
Okay. Let's thank the speaker again and the